Yeah, so when two atoms join together, we call that a chemical bond. So basically, what's happening is that one atom is doing something with the other atom, and then they have a strong force of attraction between them, and they just tend to stay together. After that, whatever they do, they're going to do it together. And it takes a lot of energy to actually spread them apart or make them do something that they will do individually. And so we call that thing because it's a very strong force, we call that a bond. All right, so there are four kinds of bondings, and we'll talk about that what are the factors that cause one bond to triumph of the other and just cause one of the forms and all that. You already know the bonds from O levels, but today what I'm going to do is I'm going to give it a different angle. So instead of knowing, we already know that when atoms share electrons or they lose electrons and they do all sorts of things. And the whole point in O levels, we said, was to get a zero in the last shell or an eight in the last shell. And now we know better. We know that that octet rule was just a simple way of explaining that S and P orbital is completely filled up. And the covalent bond was simply talking about sharing of electrons in those orbitals. And we are going to build on that concept that atoms don't have an obsession with eight or with two. All they want is a symmetric cloud of electrons. That's all they want. They want electrons to not be unbalanced because one is having a different spin than the other, but there's no other atom to counter that spin. So they just want a symmetric cloud. And what better way to get a symmetric cloud than to get a completely filled orbital? But turns out it's not that easy. For example, if you look at hydrogen, hydrogen has one orbital, one s, and that has just one electron. And another hydrogen will be a copy of this with another 1s with one electron in there. Now, the trouble is that if both of these hydrogen, they want to get 1s2. Right now, they're at 1s1. 1s2 would look something like this. They can't have that right now. So what they'll do is that they come together and they try to overlap their orbitals. What? They try to overlap their orbitals. Now, basically, atom is not a rigid thing. Atom is like a cloud of electrons that is joined together through what you call, there is a cloud of electron around a nucleus. That's what an atom is, right? So it's not that rigid. So if I were to visualize hydrogen atom, it will be a hydrogen like this surrounding by a cloud like that. And if I want to get on the other one, so it will be hydrogen like this surrounded by the other like that. Okay. Now, if I were to select this one, okay, and take this one and somehow move it closer to the other one. So we know what will happen. They will repel each other, right? If I were to take that and bring it even closer together. So what happens here? Right now, what's going to happen is that electrons are being attracted by both of them, both of the uh, what you call nucleuses. Okay. If I were to bring it even close together, which I can, the electrons are still being attracted by both of them. And now the atom is quite stable. Why? Because the electrons, the pressure on one nucleus to pull it is not that high, and both the nucleuses are working together. But if I were to bring it so close to each other that now the nucleuses are almost touching and all really, really close to each other, then what will happen? It's simple. They will repel each other, and they will repel each other with a very, very strong bond. Why? Very strong force, because positive on the nucleus will repel positive on the other nucleus. So they'll just throw it out away. But then another thing happens. These electrons, remember that this cloud is negative and this cloud is also negative. So the hydrogen here, the nucleus, is pulling on these electrons as well. Sure, it's pulling on its own electrons, but it's also pulling on the other electrons. And this hydrogen is also pulling on these electrons. So what happens? They start to come even close together now. So now they will do the same thing. It tries to come close together again. Then it tries to come even more close. and more close and gets repelled again. And then it comes again, then it repels again, and so on and so forth. Keeps on bouncing on and off and off. Ultimately, they reach an optimum level. If I were to make a graph of this, what will happen is that I have on this side, I want to know how far this is the distance between the two nucleuses. And on this side, I have the energy with which they're repelling each other, or the strength of force with which they're repelling each other. Okay. Because this energy is supposed to show the strength of force. Now, here's the thing. When they are really far away from each other, the distances are very high, the energies are really low. And as they come close to each other, the distances decrease, the energy increases. The energy is also really, really low because they're still very far away. But there comes a point where they're almost touching each other. And that is when the distances start to become really, really close to each other. Distances are so small that now they're almost close to each other. And now the energies with which they're repelling each other, they are going to be exothermic. The energy is going to be released because now one atom is entering the other atom. So energy starts to decrease and then it starts to come really close to each other. So now they're repelling each other more. So suddenly there is a high overshoot because the energy is going to be really high if the distances are very, very small. This is where the nucleuses are touching each other. And so it continues to go. And that's why it comes back. So electron or proton or this whole atom is like a ball along this path. So this ball is moving along this. Sorry, let me redraw this. So this ball is the atom. Right now it's energy. It is very far from the other one. It's moving along this path, coming close to each other. Now it's entering the other atom. This is where the sweet spot is. This is where they're optimum distance away, where energy is really low and the distances are not that high. And now it starts to go even more in. And when it does that, it gets repelled. And the energies of repulsion are so high that it skyrockets. It's very unstable. The distances are too small, very unstable, comes back, goes back, comes back again. इस तरह वो bounce करता रहता है, like, and ultimately it settles into a position where the energy is least and the distance is optimum. This is the distance between the two nucleuses. This is the distance at which they are, where the energy that they have to release is still negative and it's optimum. It's the minimum possible energy state that they can do without repelling each other very far apart. Because remember, there are two forces at play. There are protons that are pulling on electrons, and there are protons that are repelling the other protons. And obviously, electrons repelling the other protons, other electrons. So this level of energy, we call this the bond energy. And this distance between the two nucleuses, we call them the bond length. This distance is bond length. But why exactly are they doing this? Of course, protons are pulling on the other electrons and electrons are being pulled by both the nucleuses. And that is why they do it. But there's another thing happening at the orbital level. What happens is that hydrogen has always wanted to have a complete shell, 1s2. And when one hydrogen comes here with its own orbital, and the other hydrogen also comes here with its own orbital, the two orbitals overlap. Let me use a different color for this one. So the two orbitals overlap, and now they're on top of each other, sharing the two electrons. So now this hydrogen is sharing its electron with the other one. And what happens? Both of them have 1s2. So basically, chemical bonding is nothing but overlap of orbitals. So when two or more atoms form a chemical bond, all that's happening is that there's some attractive forces keeping them the way they are. There are repulsive forces as well, but they are overcome. So there is the repulsion from the positive nucleuses of both the atoms, which is overcome. And there is attraction of the electrons to both the nucleuses, which is the dominant force here, which we call covalent bond. And because it's only the interaction of valence electrons, we only look at the valence shell. So that's how it works. The orbitals overlap. So that is the main idea. So if I were to look at the bond between them, I can now say that there are 2 electrons involved. There's 1 electron here, 1 electron here. And the covalent bond is these electrons being pulled by this proton and these electrons pulled by this proton. So that's the covalent bond. It's really, really strong. And of course, if you have more than 1 electron, it's going to go like that. So the strength of triple bond or double bond will be much higher, which simply means if I take, so I have, let me show circles. So this circle is a nucleus and there is 1 electron, 2 electrons between them. Both of them are pulling on them. So this is a pretty strong force. We call it, so for example, if I were to take the example of hydrogen, it is 1 hydrogen bond, 1 pair shared between them. If I were to take 2 more, and why am I taking 2? Because I want the orbital to be complete. Now both the nucleuses are pulling on them. So you can clearly see that this is stronger. And not just that this is stronger, its length is even smaller. Why? Because more force pulling on 2 things, it will bring them closer together. So this nucleus is slightly closer to the other one, just under the influence of this force. So for example, if I were to talk about oxygen bond, this is how it is. But of course, I'm not saying that hydrogen bond is, the bond between hydrogen is larger and between oxygen is smaller. We can say that if I had 2 oxygen sharing 1 electron, the bond will be longer. And if 2 oxygen sharing 2 electrons, the bond will be even smaller. And if I were to take it one step further, let's say nitrogen. So the single bond between 2 nitrogen atoms will be longer. Double bond would be shorter. And if I had another pair of electrons in there and they were pulling on these, that will be even shorter. So and the strength increases. So down this path, there is stronger force and stronger bond and shorter length. So the bond is stronger and it's also shorter. How we show this is usually either as a single line, or we can also use this idea that there is something like that, and the other electrons just go on the sides. I'm not drawing them at the moment, but of course we haven't forgotten about them. So there's 3 pairs shared. Of course, there are the lone pairs, the ones that are outside. So of course the other ones are there. So this is one of these is dot and cross diagram. The other is the caicule structure, or Louis diagram, if you will. And that is how the bonds are going to be there. So where exactly does the force come from? The force is between the positive nucleus and the shared electrons. So this is the shared electrons, and there's the nucleus and the nuclei of 2 atoms. So these are the ones that are pulling on each other. And that pull is basically covalent bond. Covalent means co means sharing and valent means last shell. So sharing of last shell. That's where it comes from. All right. We know how to draw this. We know the basic structure of some molecules. I will share a list with you as to what that is and all that. But again, there are some exceptions to this simple idea of octet. If I were to say that they do this because they want octet, then you can bring up many problems in which that's not happening. Let me give you a few examples. For example, I mentioned AlCl3 yesterday. So AlCl3 is this. So while chlorine has 6 electrons that are not involved in bonding, and that means it has 3 lone pairs, aluminium had 3 electrons and shared all 3. Aluminium doesn't have what we call octet. Some of them, so aluminium doesn't have it. Or if you were to talk about, let's say, sulfur trioxide, then sulfur trioxide is like this. So sulfur with double bond with 1 oxygen, with the other oxygen, with the other oxygen. What is happening here? Or if I were to talk about PCl5, कल हम इसकी बात कर रहे थे Vesper में. What is happening here? 10 electrons, really? And then, I don't know, 12 electrons in the last shell being shared. What does that even mean? Like, what are we doing here? So this is clearly not octet. And then beryllium chloride, that is even weird, because what? Beryllium is in second period. It needs 8 in the last shell, but it's not having that. It's just sharing 2 electrons. So they are all defying the octet rule. And the idea behind that is that it's actually octet rule was just a work of fiction. It didn't have any real world implications to the extent that we thought it will. What's happening is, at the heart of atoms, they have orbitals. and those orbitals are overlapping and making new orbitals, which are more stable than the previous one. So there is one orbital, which is a circle basically, that has a cloud of electron in there. So this is a cloud of electron inside it. Okay. And it has one electron. And there's another one just like this one, just like this one. And what they're doing is that they're overlapping in a way that instead of having one separate one here, they now have sharing, and not just sharing, the other one pairs it up. So it is much more stable that way. So this is an atomic orbital, and this one is a molecular orbital. And this orbital is more stable because there's a region of space where the electron can come in. By the way, the molecular orbital is just this part in the middle. Okay, so if I were to highlight it, this part in the middle, that is where the molecular orbital is. Because, and this one we call sigma, the first one. So sigma is a molecular orbital. It's an overlap of orbitals, and not just any overlap, it's a head-on overlap. So head-on overlap. And then there can be so multiple forms. So let me show you a diagram to show ki kis tarah se hoega. So there can be overlap of P, there can be overlap of S, there can be overlap of P with the other P. So you can see over here that hydrogen, it has S and that S, so they're sharing this. And then there is hydrogen sharing it with chlorine, and chlorine has a P orbital. So there's that. And then chlorine sharing with chlorine, both of them P, making another sigma of chlorine and chlorine. And not just that, you can also have a sideways overlap. We talked about it. So you can have something like oxygen, which has already shared one of them, and here it's sharing the other one. So now there is a sideways overlap. So this is a sideways overlap, that there is P, which is right opposite to the other one, not adjacent, not in the same. So it's perpendicular, if you will, to the horizontal. So vertical planes coming in, or it could be in the Z axis even. So it's like the pi bond is a sideways overlap. So this is a pi orbital that you're getting, this one. And this is a sigma orbital that you're getting, this one. So basically, here's how it happens. So if I were to take the example of carbon from your book, then this is the diagram from your book. So it says that you have two carbons, both of them in P and P, and the carbons come together and they are overlapping over here. And now you can see that they are making what you call overlap like this. So यहाँ पर आपके सामने they are overlapping in this region, and that region has now created new orbital. So this is the new orbital that is happening because it's formed from this overlap of these. And this electron cloud, a new one, this, which we'll call a lobe, if you will. So this lobe has been made because of sideways overlap of these p electrons. So how would it look like if you were to look at it? So if you were to look at it from the side, it will look just like this weird cloud of things like that, like an 8, a longer 8, if you will. And your book has a really interesting picture on this, that if you were to look at it before the reaction happened, this is what you will see. But after the reaction, this is how it will look like. So you can clearly see that it is more like up and below instead of all around and all that. Okay. So that's what a pi bond is. So interestingly, the sigma bond varies from pi bond in two ways. Number one, sigma bond is made in a different way. Sigma bond is made by head-on overlap. It's like you coming and hugging a friend of yours, सामने सामने से, and then somebody giving you a side hug, another friend. So वो side hug जो है ना, वो आपका पाई है, वो side से आ रहा है, वो उतना strong hug नहीं है जितना आपका दूसरे वाले friend के साथ है. And I don't know if that's a good example or not, but just an idea of what they should be like. Now, here's another thing. The sigma bond also differs in another way, that sigma bond can rotate. Because what happens is that, for example, if I were to take the example of carbon and this other carbon, or let's suppose मेरे पास इस तरह से ये carbon है, okay, and I have chlorine here, I have hydrogen here, chlorine here, hydrogen here. So I can rotate this whole side, just give it an upside down rotation, and that is fine with the carbon's bond with the other one. So I can do this, that this chlorine is upar or this chlorine is now niche, and that is fine. The rotation can occur because basically sigma bond is nothing but this whole region. So region वहीं का वहीं है, no problem. But let's say we don't have this. Instead we have something with a pi bond. So pi bond would look something like this. So if I have the same example, but instead of having chlorine here. Now here's the thing. My sigma bond is the region inside them, between them. And my pi bond is the region upar niche. Again, I'm just talking about carbon wala. The angle is 120. So now I have this region where the pi bond is between these two, the double bond. Now here's the thing. If I wanted to rotate this, now I can rotate the electrons that are in the red region because they're still there. But the moment I try to do it, so if there's an electron here and there's an electron here, it can't rotate. It can't come down, because to come down, it has to first go right. उसको पीछे जाना पड़ेगा और पीछे से होके नीचे आना पड़ेगा. Do you get it? That it can't go directly ऊपर से नीचे ऐसे jump नहीं कर सकता क्योंकि बीच में दो electrons बैठे हुए हैं. So it has to go to the side and then come back. It has to take a detour. And that would mean that the overlap has to first break. जो उनका overlap हुआ है, वो it has to first break. It is not possible for me to take the yellow portion at the bottom and bring it ऊपर without having to first break the overlap. क्योंकि वो साइड से होके जाएगा. एक मेरा ओवरलैप ऊपर है, एक नीचे है. नीचे वाला ऊपर नहीं आ सकता जब तक. You don't get it. Okay. So here's the thing. So I'll try to show it to you as a video if I can. Let's see. I have this phone. All right. So this phone is here in front of it. And I have, I don't know. What do I have? I have this small wire. So this small wire, I have it on one side of the phone. All right. So ये ऊपर है, ठीक है? यहाँ पे है wire. I want to bring this wire यहाँ पे नीचे. Okay. So I can't go on the right and left because वहाँ पे ये nucleus है. यहाँ पे nucleus पड़े हुए. I have this wire. I want to bring it नीचे. How do I do it? The only way possible is I can't go into the phone. यहाँ नीचे नहीं खींच सकता मैं इसको. The only way possible is I take it to the forward side or forward से नीचे ले आऊं. और ये यहाँ पे है, I bring it either पीछे को और पीछे से नीचे आऊं. And that's not allowed. Because the moment I try to do it either पीछे को, I have brought it to the area where the third p orbital is. क्यों? Remember, there is a p orbital that is on the x, there is a p orbital that's on the y, and there's a p orbital that's at z. एक आपका लेफ्ट राइट में पी है, एक ऊपर नीचे में पी है, और एक आगे पीछे में पी है. सो द ऊपर नीचे वाला this one cannot go, ये ऊपर है, ये नीचे नहीं आ सकता जब तक ये साइडवेज वाले से गुजर के नहीं आए. ओके, दैट्स कोको. ओके, एंड जब तक ये वहां से गुजर के नहीं आएगा वो रोटेट नहीं कर सकता. And that rotation is not allowed because then it will be overlapping with another orbital. तो ये वाला orbital क्या करेगा? It has to first break this bond. पहले इसको तोड़े, फिर ये अब free हो गया, अब ये घूमता रहे और फिर ये नीचे आ जाए. This rotation isn't allowed because it will have to first break जिस P में ये पहले से था, and then it will go in the second one. So because of this rotation not being allowed, the sigma bond wins in a way that it can rotate, but pi bond cannot rotate without first breaking. So if you want to rotate the pi bond, you will have to first break it and then make a new one, which is not allowed. Which means that if I were to make this molecule like this, कि ये हाइड्रोजन राइट साइड वाला हाइड्रोजन ऊपर चले जाए और राइट साइड वाला क्लोरीन नीचे आ जाए, then these are not the same. They are not the same. ये दोनों सेम है, ये आइसोमर्स बन गए हैं. They are two molecules with different structures, and obviously because of different structure they will have different properties. So rotation is not allowed in pi, which means that when you have double bond or triple bond, the rotation is not allowed and you will be creating newer molecules, newer compounds if you were to rotate them. All right, so let me try to show you a molecule based on how its orbitals look like. So here I have, there you go, this is ethene. Its three-dimensional structure would look something like this. So what I have here is that if you were to look at the formula, this is C2H2, okay, C2H4. So this is what the bond is. So this is a sigma, the green one. This is another sigma. This is a sigma, and this is a pi that's going to form. And that's just one bond. So I'll just draw one. And this is a sigma here, this is a sigma here. Now, if I were to just show you the pi one, तो pi वाला कुछ इस तरह से नजर आएगा आपको. If you were to just look at the pi one, this is the one. So I've converted the green ones to these wedges and dots. A wedge means it's towards you. Like अगर आप screen को देख रहे हो तो screen से बाहर निकल रहा है, ये आपकी तरफ है. And the dot means it's inside, into the plane of the screen that you're looking at. And this solid line means it's on the screen. So this is called the three-dimensional formula, where the dot means inside, wedge means outside, and solid line is on the screen or paper. And this is the pi cloud that is around it. So you can't bring the top pi cloud niche ko without having to first break it, which means rotation is not possible in this. So this is different from this one, for example. So this one is, guess what it is? So if I were to make the three-dimensional structure of, so can you guess which molecule I'm talking about here? You can see that the bond is 109.5 because carbon has four sigma bonds, one with each hydrogen. So this is ethane, okay, which is very different from the ethene molecule that we saw, which is like this. So this is the ethene molecule, and I'm just showing the three-dimensional structure, and you can see that the pi cloud is ऊपर और नीचे. So अगर आप इस molecule को भी देखो ना तो आपको pi cloud बहुत फैला हुआ sides पे नजर आएगा, ऊपर और नीचे. Okay, like जो सोचो आपका बर्गर के buns नहीं होते ऊपर नीचे वाले, ये वो है. So that is how it is as far as the electron is concerned. Let's try to imagine what a triple bond would look like. So triple bond, I'm drawing the ethene one. So this is what a triple bond might look like. So if you look at it, what's happening is that there is one blue sphere upar and niche. So there's one upar, one niche. That is supposed to show 1p. So this is, let me call it py, and this is py, and this one, this is pz. So एक बाहर को है और एक अंदर को है, पीछे को, जो इस वक्त छुप गया. And if I were to just isolate the p orbitals after they made the bond, so they will look something like this. कि एक आपका ऊपर और नीचे है और एक आपका आगे और पीछे है molecule के. And they're just surrounding like a Subway sandwich. The two वो जो bread के pieces हैं, they are the ones around it, और जो बीच में filling है, that is your sigma bond. So that's a triple bond, or what it might look like at the molecular level. Okay, so do you get it that it's actually the orbitals that we are trying to fill in? It's not octet anymore. We're just looking for orbitals, और अगर orbital fill हो रहा है, हम उसको fill होने देंगे. So let's take the few examples that I gave you which did not follow the octet rule. So I gave you the example of aluminum trichloride. I gave you the example of beryllium chloride or phosphorus pentachloride or sulfur trioxide. So let's look at their structure to see कि हो क्या रहा है वहाँ पे. So aluminium has a basic last shell like this. So there is the last shell which goes like 1, 2, and 3 like that. But remember we talked about that to get more electrons or to accommodate more electrons, it's possible to move one electron from one orbital to another one. So यहाँ पे वो होगा, it will create hybrid orbitals. We'll talk about hybrid orbitals later on. So when it starts to bond, it has a structure like this. Now you can see that there is a space here, there's a space here, and there's a space here. ये orbital हमारे पास एक एक electron इधर आ सकता है. And if you look at chlorine, that chlorine has, if you were to look at the last shell, so chlorine has this. So chlorine has a space here. And that's what happens. Aluminium का एक orbital इधर से इस chlorine के साथ overlap कर जाता है. And that way, what happens is that you get aluminium trichloride. That aluminium's one orbital is overlapping with chlorine's the other one, the last one. And now both of them have a complete orbital. And because of that complete orbital, hota kya hai? That these electrons have opposite spins to each other. And because of that opposite spin, they cancel each other's effects, electromagnetic effects. और उसकी वजह से the cloud is symmetric. But जब cloud symmetric होता है, it's less susceptible to attack. It is more stable, if we were to use that word. So that is what they try to do. So aluminium ने अपना एक इलेक्ट्रॉन इसके साथ इस तरह से शेयर किया है कि उसका ऑर्बिटल ओवरलैप की वजह से कंप्लीट हो जाए. So if I were to take chlorine, so एक क्लोरीन ने यहाँ पे कर दिया, एक क्लोरीन ने यहाँ पे कर दिया, एक क्लोरीन ने यहाँ पे कर दिया, and there you go. Aluminium has filled 3 of them, and that's good enough. Now let's look at beryllium. ऐसा क्यों करता है? So beryllium has 2 electrons in the last shell, the 2s2. But p उसका है तो सही, चाहे वो खाली है. So what beryllium does is takes one of these, brings it to the other one, और क्लोरीन आता है और क्लोरीन इसको फिल कर देता है. तो क्लोरीन का एक p ये वाले को फिल कर देता है और क्लोरीन का एक p ये वाले को फिल कर देता है. And that is how you get beryllium dichloride. So that's what happens. Sulfur ऐसा क्यों करता है? Because sulfur has d orbital available. D orbital can accommodate a lot of electrons, more electrons than this one can. So d orbital does that. Sulfur अपना d orbital open करता है और वहां पे इन electrons को move कर देता है, जिसकी वजह से it gets what we call expanded octet. And why is that happening? Because if you look at it, phosphorus is in group 5, right? So phosphorus can have 5 orbitals जिनमें वो एक एक इलेक्ट्रॉन डाल दे तो वो 5 बॉन्ड्स बना लेगा. क्यों? क्योंकि each one of those orbitals can bond with another one by overlapping and sharing another orbital. Sulfur is in group 6, so sulfur can accommodate 6 more electrons क्योंकि उसके पास 6 हैं. वो उन 6 को एक एक ऑर्बिटल में डिस्ट्रीब्यूट करता है. वो कैसे करता है वो हम बाद में देखेंगे, बट वो पोटेंशियली उन 6 को डिस्ट्रीब्यूट करके हर ऑर्बिटल में एक एक ऑर्बिटल अपना इलेक्ट्रॉन रखा, एक इलेक्ट्रॉन किसी और का पकड़ा और ओवरलैप कर लिया. So how do things make double bond? They just take 2 orbitals of each other and overlap them. How do things make triple bond? They just take 3 orbitals of each other and overlap that. Let me give you an example of nitrogen here. Nitrogen के पास हमारे पास nitrogen has this, right? And the other nitrogen also has this. So what the other nitrogen does is कि उसके पास अपने ये दो ये वाले तो हैं ही, वो अपना p इसके साथ ओवरलैप कर लेता है और एक p का इधर, एक p का इधर और एक p का इधर. तो दोनों को लगता है कि हमारा ऑर्बिटल फुल हो गया और वाकई फुल हो गया. They have shared this and they have done it in a very elegant way. The orbitals of their last shell are now complete, and that is how they're stable. They have formed triple bond. So what is a triple bond? When they're sharing, they're making 1 sigma and 2 pi. How are they doing that? 1 sigma because of head-on overlap. तो let's suppose इसमें से पहला वाला 1 sigma था, तो इसका px और उसका px ओवरलैप कर गया. अगला वाला इसका py और उसका py साइड से ओवरलैप कर गया और इसका pz और इसका pz साइड से ओवरलैप कर गया. And that way you get a sigma bond, a pi bond and a pi bond. A bond now is nothing but an attempt to have symmetric cloud. और उसमें होता क्या है that they overlap orbitals. So now when we say that the bond is made through sharing of electron, what are they technically doing? They're overlapping their orbitals. They're aligning them in a way that the orbital gets filled up, and now they're able to have a symmetric cloud. But still bond क्या है उसके अंदर? Bond तो एक force का नाम है ना. तो वो bond क्या है? वो bond कुछ भी नहीं है. वो एक strong force है एक atom के nucleus की दूसरे atom के nucleus की और उनके shared electrons की. So what's a bond? It's a strong force of attraction between the two nuclei and shared pair of electrons. And how is it formed? It is formed by overlap of orbitals to complete them. Now here comes a question. By the way, यहाँ तक किसी को कोई question, कोई confusion? Great. Now here's a question. Can those things which have an empty orbital make a bond? For example, if I look at aluminium here, aluminium has made a bond with one chlorine and with other chlorine and another chlorine, but there's still this orbital which is completely empty. Can this make a bond? A bond is nothing but a way of fulfilling or completely filling an orbital. That's it. That's it for today. We'll continue on to build on this topic. I know this was a lot of things to absorb, so take your time. We will review most of these concepts again tomorrow by adding something there. Any questions?
Sir, so an empty orbital can make a bond.
How would it make a bond?
Sir, your voice broke. Could you repeat that?
I'm saying, how would it do that?
So maybe by overlapping with the orbital that already has.
Yeah.
Yeah,
Overlap.
absolutely. That is exactly what happens. That one empty orbital, because they don't care कि electron कहाँ से आए. All they need is two electrons to fill an orbital. वो दोनों कहीं से आ जाएं बस ठीक है. Whether they both contribute or whether one of them contributes doesn't matter.
Sir, but isn't that then a dative covalent bond?
It is a dative covalent bond, which is no different from other covalent. All right, take care. Allah Hafiz.